Welcome to The Explainer. Right now, there is a massive transformation happening right beneath our feet. We're moving away from those traditional, highly centralized power plants to a vastly distributed, fully digital energy network. It's incredibly exciting, but with this amazing innovation comes a hidden fragility, one that could fundamentally threaten the stability of our entire power grid if we aren't paying close attention.
I want to hook you immediately with this incredibly provocative quote from our source material today. What is truly dangerous is not the vulnerability itself. It is the massive centralized system that assumes it is safe. Think about that for a second. It perfectly captures the core paradox of modern infrastructure security. We spend so much time, energy, and money trying to build these impenetrable walls. But the real danger? It lies in the blind confidence that those walls will never fall.
Okay, let's dive into this. To understand this paradox, we have to first accept that we are fully living in the energy IoT era. Our power grid is no longer just a collection of dumb wires and spinning turbines. Energy equipment today is fundamentally digital. Power generation has officially become an information technology issue just as much as an electrical engineering one.
Modern distributed energy resources, or DERs as they're called in the industry, are no longer standalone pieces of equipment. A solar inverter on your roof now actively connects to an output control server. An energy management system is constantly aggregating demand and generation data. Your EV charger uses web APIs to handle billing and load control. These are highly connected digital networks. They're industrial IoT devices relying on IP connections, meaning they are incredibly smart, absolutely, but they are also entirely vulnerable to cyber threats.
To combat this vulnerability, governments and industry bodies are stepping up. Take the JC Star label from Japan, for example. It acts as a much-needed baseline for IoT product security. It prohibits the bad stuff, like default passwords, ensures proper access controls are in place, and mandates vulnerability response contacts. It is an absolutely essential first step to ensure that the equipment we're connecting to our grid meets at least basic digital hygiene standards.
And look, this isn't just a theoretical exercise. It's a real, tangible policy shift. Starting in April 2027, large-scale solar and battery systems will actually require this kind of certification just to be legally allowed to connect to the power grid. It's a massive regulatory push to finally raise the floor on cybersecurity across the entire energy sector.
But here is our first major pitfall. A label can create a really dangerous false sense of comfort. It's kind of like a car passing its annual safety inspection, right? That sticker only proves the vehicle was safe the exact minute it left the garage. A certification is just a point-in-time snapshot. But an energy network? That's a living, breathing system. It undergoes constant API updates, cloud modifications, and new operating rules. A static label simply cannot guarantee the safety of a dynamically changing real-world environment.
So, the crucial point is understanding the concept of a trust boundary. In industrial control security, this is the design perimeter between your trusted internal network and the untrusted outside world, like the open internet. Defining this boundary is literally the first major hurdle in securing a power plant. Why? Because it determines exactly where you enforce strict access control, and conversely, where you must assume the environment is hostile.
But let's look at the messy reality of an actual physical solar site. It's not a clean, simple box neatly separated from the internet. It's a chaotic system of systems. You've got inverters and data loggers, EMS platforms, localized sensors, and then, inevitably, someone adds a maintenance Wi-Fi router or an IP surveillance camera to the network months later. The clean theoretical definition of a trust boundary completely blurs here. Where exactly does the certified safe zone start and stop in that mess?
Which brings us to a rather unsettling question. When new devices are constantly being added to a site, who continuously monitors the certification boundary? Think about it. If a site engineer plugs a non-certified laptop or a cheap, off-the-shelf commercial router into the solar plant's local network, that static certification label on the inverter means absolutely nothing. The boundary has already been breached from the inside.
This over-reliance on certification leads us directly into what the source material calls the centralization trap. When we assume that simply getting a label makes everything inherently safe, we tend to design highly centralized systems to manage all those safe devices. We end up creating massive, standardized architectures where millions of certified devices operate identically. And standardizing millions of devices? That creates the ultimate single point of failure. If every solar panel and battery in a region relies on one cloud, one identity infrastructure, one over-the-air update mechanism, and one API, well, you no longer have a decentralized grid. What you have is a massive, physically distributed but logically centralized target. One single breach in that cloud doesn't just take down one smart home, it cascades across the entire power grid. Now, what's really interesting about this concept is how digital risk translates directly into a terrifying physical reality. The threat here isn't just about data theft or a privacy breach, it's the physical threat of synchronized control. If an attacker gains access to that single centralized control screen, they literally hold the power to manipulate the physical flow of electricity on a massive, coordinated, region-wide scale. A simultaneous shutdown by a hacker is an obvious threat, right? It leads to an immediate loss of power, blackout. But a simultaneous load pickup, that is just as terrifying. Imagine millions of electric vehicles acting like a stampede, reconnecting and resuming fast charging at the exact same millisecond after a temporary outage. That massive, simultaneous power draw will crush the physical grid just as completely as a malicious shutdown.
So, how do we fix this? Well, we have to admit that perfect defense is a fantasy. The attack surfaces are simply too vast. We must pivot our thinking entirely to the solution, resilience by architecture. We need to stop pretending we can build an impenetrable fortress around our energy grid, and instead start designing exactly how our systems will behave when they inevitably break. We must fundamentally shift our paradigm from certification-centered thinking, which is static, assumes complete protection, and relies heavily on the cloud, to resilience-centered thinking. This means we design for dynamic, continuous observation. We design for graceful degradation rather than a sudden, catastrophic collapse. And most importantly, we design for local autonomy and offline-first safety, moving far away from centralized management.
To put it simply, we are shifting from centralized control to self-protection. If solar panels, EV chargers, and home batteries are going to be the backbone of our society's infrastructure, they cannot be mindless drones waiting for instructions from the cloud. The nodes in our energy grid must have their own reflexes. They have to be able to survive even if the central brain gets cut off or compromised.
And this brilliantly illustrates the core conflict, the abstract cloud state versus the physical on-site reality. An autonomous node must be programmed to ultimately trust the physical measurements, the actual, tangible voltage, current, and frequency right in front of it, over any abstract command coming from a compromised or glitching cloud dashboard. Physics has to win out over software.
So these are the foundational design principles required for this kind of robust, autonomous energy system. We absolutely need local autonomy and distributed intelligence, so decision-making actually happens at the edge. We need offline-first operation, ensuring the system functions perfectly safely without an internet connection. And it must be fail-safe, meaning when it breaks, it fails into a harmless state, smoothly degrading its operations, rather than just shutting down entirely.
Let's step through exactly how this works in practice with a local fallback process. First, the local equipment detects a frequency or voltage deviation on its own. Second, and this is the real game changer, it actively rejects any conflicting commands from the cloud that might be telling it to ignore the danger. Third, it limits or stops power output to protect the local grid. And fourth, it isolates itself to maintain only critical local loads, keeping the lights on for the essentials.
This entire philosophy really boils down to one simple idea: designing how the system breaks. Resilience is not about preventing failure entirely. That's impossible. It is about creating smart, predefined state transitions that localize the impact. When a cyber attack happens, the damage should be contained to a single device or a single site, rather than ripping through the entire national grid like a wildfire. An autonomous system has multiple layers of fallback options. It's never just a binary choice between everything is perfectly fine and total blackout. A node can smoothly step down from normal operation to a local degraded operation, then to output limiting, all the way down to a limited islanded operation where it runs completely disconnected from the broader grid well before it ever resorts to a full manual shutdown. Now let's be very clear here. The cloud is still amazing. We're not saying get rid of it. It is unparalleled for wide area optimization, energy market trading, and weather forecasting. But we have to treat the cloud and internet connectivity as a convenient nervous system, not a life support system. Our physical energy assets cannot, under any circumstances, rely on an active internet connection just to operate safely. Therefore, there is a minimum public guarantee that must be hardwired locally into every piece of energy infrastructure.
No matter what manufacturer you buy your hardware from or what fancy cloud service you use to manage it, local physical safety parameters, things like frequency deviation protection, overvoltage protection, anti-islanding safeguards, and fire prevention, they must be guaranteed to work independently, right there on site.
We've covered a lot of ground today, from the real limitations of static cybersecurity labels like JS to the absolute necessity of building self-protecting, autonomous grid nodes. So as we wrap up this explainer, I want to leave you with this final vital question to ponder. In the era of distributed energy, when the cloud inevitably disconnects, how will your grid survive? Thanks for exploring this with me today. Keep learning, and I'll see you next time.